Okay, good morning everyone. And thank you very much for coming. For the first time I'm seeing many faces which I have never seen before during my classes. And I really sincerely thank you for coming in this short notice, very short notice. I can see the seriousness of the exams, and the cartoon really professes why you are here now. Okay, so I would like to keep the lecture, this session very short, and I will go through probably almost all the questions today. Both the 2010 resit papers as well as the semester 1 exams. Okay, is that okay with you? It's close to around how many? 6, 6, 12, 12, about 24 questions. Okay, I'll quickly go through that. And as I mentioned every time in my lecture, if you have noticed or not, the questions will be coming only from my slides, which I pointed. I've said many number of times. Okay, the questions will come from the notes or the slides which I provided. There may be very small deviations, not much, very small deviations from the current one, from the slides. Very small deviations. It won't be, but looking at the assignments which we did, I really give a good credit to you. You did a really good job. So I don't see a huge panic in your exams. Okay, and the exams questions are very easy for you guys. So that's an encouragement. So I haven't said the tough questions. No, not much physics either, but some there. There were email concerns asking about whether we will be provided any equations or formulas. I'm afraid the answer is no. Okay, there's no us or us. That will not make a difference to me. Okay, so you have to know. You have 12 classes, right? 12 classes, 3 hours. Lots of energy went inside. So you have to know. You have to know the equations. Okay, you have to know that.
Can we know what topic is going to come up at least? Is it good?
Is this an indirect way of asking me what questions you have?
There's a lot of formulas to remember.
No.
There's a lot of stuff to cover as well.
Okay, tell me what are the lot of stuff we have to cover.
Sorry?
Tell me, you have solar, you have wind, okay, you have biomass, geothermal, and what else? The interaction, right? And hydro, okay. And if you see the equations, I haven't put many equations there. It's only relatively few, right? And when I teach, I did explain that. Did I or not?
You know the equations that you put up on Moodle? I printed it out there. Is that basically all the equations we're going to need? Because I've been doing the questions.
Throw me the paper. I don't know what I did.
I've been
Okay.
doing the questions.
This is really an indirect way of pulling my leg. That's why I said I'm going to concentrate on this. Okay.
I done the question on Stephen's page, isn't it? I think I didn't want, and it required a lot more formulas.
What did I say to you a few minutes back?
It's going to be all from the slides.
For the slides which I prepared, right? That's what I said. Did I?
Yeah, you did, yeah.
So
So
exactly follow what I said. Okay. Say no more. Okay. Say no more. Right?
So that looks.
I won't say anything.
Yeah.
I won't say anything. I told you what I did.
Okay.
Huh?
That looks like this is.
I'm not telling you anything, okay? I'm not telling you anything, okay? But that's not hugely different. You did Carnot engine there before, right?
Sorry?
I did do Carnot engine. Some of the Carnot engine and Stephen Boltzmann constant.
Oh
Yeah. And he is showing the equation which I already thought. Show me something different. I agree.
Yeah.
Okay.
Is it going to stay like the question, the topic, or are you mixing matching in the question?
No, it will be staying on. The first question means if it is solar, it is solar. Second question, if it is biomass, biomass. If it is wind, wind. So A, B there, right? Say for example, if I take the semester 1, oh Jesus, what I have to do here? I forgot, keep the current color scheme, but ask me again if the computer performs. keep the current theme. Don't show this message again. I hope it works. Okay. So if you take the paper, right, the 1A and 1B, right? So if I put the question on solar, it will be on solar 1A and 1B. I won't be mixing and matching. It doesn't make sense. Okay? So if you want me to do, it's too late for me to do. Okay? So that will be there. Okay?
How many parts could be the questions? Are A, B, C, or just A and B?
I don't remember what I did actually. Sorry. Most likely it's A, B, and hardly one, maybe C there. I think A, B, C. Because if I put C there, then the questions are like the marks for A, B, C will be less, right? 4 marks, 4 each, something like that. Okay?
That's one.
There's no panic, lads.
It's an A and a B.
I told you before, you did a really good job in your assignment, so no panic. It's a cakewalk. Yeah, you would be. Don't give me the other surprise, okay? Having done the assignments well, if you're not going to do the exams well, I'm going to really kick your ass. As simple as that, okay? Is there anything before I start?
Yeah, you have to have a copy of the exam paper there.
Yeah, you want to take these exams? Okay? But then you have to, what do you call, you should have attended this exam last year. Then you can use this. Right. So, just repeating, most of the questions will be asked from the lecture notes only. Okay? And equations and formulas will not be provided for exams. Okay? And there's not a hell of a lot of things, man. It's 6 questions. Okay? 6 questions. And most of the guys, you already came to the exams, already came to the lectures. So you know what it is. Okay? Right. I'll just go to quickly to the previous exam questions. That's what many people are asking actually. I got 36 emails asking me only solutions for the examination questions, previous examination questions. Okay? So that made me to feel that I should quickly go through this. Okay? So I presume you have the previous exam questions on your hand now, all of you. Do you? Everyone has that, right? Or I have one copy here if you want. You have it, is it? You don't? You can get it from here, and you have it. Sorry, you can share it. So almost everyone has the question, right? Right. Okay. Okay, let's start. Explain the term Hubbard's peak and outline the potential consequences of the future market. Straightforward, right? Guys? So, initially I thought of doing this, then I stopped it. I prepared only 4 slides, then I can go through by word. So you know that slide number 12, these are all silly things which I stopped doing it. Slide number 12, class number 1, introduction, you know the bell-shaped curve, right? Yeah, that's Hubbard peak oil. And the consequences and the projections you can easily do. What happens and why the peak oil happened and how it affected the energy market. And even you can also go in how the future energy market was troubled by Hubbard's peak, and is there any other peak oil which you can realize. Okay? So that's very straightforward, right? Hello? Yeah? So you don't need me. Right? So okay, at the halftime in the World Cup final, 1B, that's 10 marks, lads. That's 10 marks. I can see that. That's a cakewalk for you guys, if I ask the question. Okay, at halftime in the World Cup final, 300,000 1 kilowatt kettles are used for boiling water. Each kettle takes about 3 minutes to boil. All of this takes place over 30-minute period, with energy drawn from the grid approximately uniform over the 30 minutes. If you needed to store the energy needed to boil all those kettles in a pumped hydro storage facilities, how large a work volume would be needed? Assume a head weight of about 500 meters and energy efficiency generation is 90% and the density of water is 1000 kilogram per cubic meter. Okay, what do you need to know in this? Tell me. Say again? Kilowatt hour. Okay. Power. You need to know the power, right? So the power is already given, right? 300,000. I mean 300,000. That's the power kilowatt. Okay. So from the data, I think probably this is the only slide I did the equations. I think. Okay. From the data provided, approximately 30,000 kettles, right? Every 3 minutes over 30-minute period. So 300,000 kilowatt hour over a 30-minute period. So you know the equation Q. That's what we need to know. Power output is P over eta rho g, the density, gravity, and h. So if you put all these things put together, you hit 6.66 meter cube per second. And then you need to know the volume, how much volume it is. So the volume is QT. So that's what it is. Okay? 12K, and this is 10 marks, I think, if I'm right. Or 5 marks. Okay, that's why it is. In fact, I would have given less than 5 marks. Okay, that's the end of the slide. So, right, shall we move on? So the next question is, explain the learning curve concept. Okay? Learning curve concept and how it might be used to predict future change in capital cost products based on the emerging technology. So I'm not taking this question because I haven't teach you that. Okay? Hello? Still in that slide. Okay, okay. You finish it up and then let me know.
Sorry, will you be uploading this?
Solutions? No. No. No, I won't upload the solutions. No. No, that's it. I have only one this. After that, I stopped doing the slides because it takes me a lot of time to do this. But rather than I can quickly go for an interactive session. That's it. So that people can pick it up from the audio. Right. So once, sorry, 1C is there. Sorry, I forgot the 1C. So given the most renewable energy resources are intermittent in nature, storage technology is key. Identify and briefly discuss the primary factors you would consider in evaluating the potential storage. Right? This we have thought. Okay? So given that the most renewable energy resources are intermittent in nature, storage technology is key. Identify and briefly discuss the primary factors you could consider in evaluating the potential storage. So the answers is the response time, energy density, environmental impact, and if you're going for a charge, batteries, it's charging time. So you can, these are all the preliminary, okay? You can have anything which you can justify. I can accept it. Okay? Is it okay? Response time, that is milliseconds. What is the response time? What is the energy density? That is size and the space requirements. Environmental impact and the charge time if you're using a batteries. Okay? And this is just a gist of the list. You can also have are there any other key factors which you think responsible and which is falling within the regime. Definitely I'll accept it. Okay? Is it okay, lads? Next question, okay, fine. So explain question number 2. Number 1. So explain the learning curve concept and how it might be used to predict future change in capital cost of products based on emerging technology. So I don't think I covered this. But now it's straightforward. Immediate no, man. I thought you were saying, oh, no, you did. Immediate no. That's fine, okay? So I haven't, so you know that the clue, I haven't asked this question. So I can tell you that I haven't asked this question. Okay? The first unit of a wave energy device costs 100,000 euros. The system expected to follow a progress ratio of 0.83 learning curve. What is the cost of 100th unit? Okay? So again, the 1 and B are the same, pretty much, the learning curve. Okay? So take it out of the equation immediately. Okay. Identify and explain key design and performance or criteria of wave energy device. Yeah, this we did. Okay? Anyone wants to volunteer? Anyone wants to volunteer? Come on, guys. identify and explain the key design and performance criteria of wave energy device. Okay, there are quite a few there, okay? The thing is, you need to talk about the survival, you need to talk about the deep water, lifetime on site, self-reacting point observers, arrays, tuning and control, significant installation capacity, and what is the power capacity of these. So there are few bulleted points you need to target, and fabrication, cost, health and safety measurements. These are all the key design and performance criteria factors affecting the wave energy device. Okay? I don't want to go through each and every subtitles because it's all there. You can get it up. Okay, 3A is
Sorry, Satesh, that question 2B, all those design criteria, was that in the notes?
sorry?
Was all that in the notes, the design criteria for wave
It should be there in your wave energy class. Yep. Is it not there? Okay, I'll come back to you, okay? You keep we park the question if there is any doubt, okay? I'll go through the others, okay? Sorry, what's your name?
Dave.
Dave. I'll go through the question, okay, with you, okay? So that I'll quickly fill the other things, okay? Okay, explain with the aid of PN junction and how can be used to convert the solar energy radiation. Question 3A. I'm on 3A. So explain using the aid of PN diagram how PN junction can be used to convert solar radiation into electricity. That's a straightforward question which we did in the solar energy class, solar photovoltaic class, right? How you do the barrier. Is everyone clear with that question, right? You know the clear question is clear. The answer, everyone knows the answer, right? It's there in the notes.
Yep, it is.
Yeah, it's evidence. Okay, so do you want me to go through that, or we can go to the next one? You want me to go through it? Oh, okay, who's having the slides? I don't have the slide in my hand. Okay, or okay. I don't like you, man. Who's that guy? You said, right? I seriously don't like you. No. Which one? Which lecture? What is it? Lecture 6?
6, 7, 6, 7, 8.
Is it in the 8 or 6? I don't know. I don't remember which lecture I. Yeah, that's it. That's PN junction also, right? Quick review of the last, so it should be 7. Okay, you can also use this PN junction. What it is? P type silicon. N junction as well. So you can also use this slide, and what are all the basic things are there? It's already there. The basic steps involved in the solar cell: charge generation, collection of electricity, generation of voltage, dissipation of power. I'm not going to go through all these things seriously because it's already I have spent a lot of energy on this. Okay, so you go through your notes. I don't think I have. Okay, so the other thing is the next part: define and explain fill factor in a solar cell. Okay. So with this we extensively covered, right? From the current slide. Oh, come on. Okay. You know what is fill factor here, right? Okay, this is efficiency. This define and explain the fill factor. Define and explain the term fill factor for a solar cell. So you know what it is, how the efficiency has been defined, and what is the ratio. That ratio gives the figure of merit, that is fill factor. Okay? And then you can also derive the efficiency from this. So I won't expect more than this in 7 mark question. So you have to define and explain, and if you want to put this diagram as well, you can do that and explain how the fill factor works, and then you can show the efficiency. Okay? Right. Next one. The IV characteristics of a solar cell driving 3 ohm electric load is given as follows. Are you in there? 3B? Okay. So, this I haven't covered, but it is very straightforward to explain as well from this, from your fill factor thing, right? Equations. From the fill factor equations. Anyone have any idea? The IV characteristics of solar cell driving 3 ohm electric load is given as follows. As follows. And it's about 700 watt per square centimeter. What is the efficiency of the solar cell circuit and fill factor? Can you derive? Can you let me know how you do it? What is the P out?
Power is VM by IM.
What? What is the P? Power output is IV, right? Okay. And maximum power delivered to the load when IV in a rectangle. This is you have that. It was very clear that you have a rectangle, right? You have a rectangle given. You have a rectangle given here, right? You take the question paper. You have a rectangle given. So so what you have to do is maximum power delivered. IV is maximized by IM, as you said. Okay. I is nothing but IM. V is VM, right? Hello? Yeah? Don't sleep, man. I know that you are sleeping in the class. I know that. Okay, don't sleep here. Okay? The fill factor, the figure of merit of the solar system is, you know that the equation is here. So, IVM, right, by ISC and VOC. That's a fill factor. So, plug and play. Want to have a FF close to unity as possible. That's what the theory says, right? FF should be 1. If you show the graph. So, figure of merit. So, typical value of FF is 70 to 85%. So, depending on the device and structure, whatever you want to plug and play. Right. So, IV is how much? Approximately from the diagram. You know what I and what V, don't you? 74.6 milliwatt. Okay. And input from the sunlight is nothing but light intensity into surface area, which is 700 watt per square centimeter. And the surface area is how much? 0.03 ohm. 0.03 meter. So that's about 0.63 kilowatt. So from this, if you get, the efficiency would be around 11.8 and figure of merit will be around 72%. Okay? That's what you will get if you do the equations properly. Okay. Did we do this problem in our class? The wind one? Calculate the power in a wind with a speed 5 meters per second incident on a wind turbine with blades 100 meter diameter. Assume the density of air is 1.2 kilogram per cubic meter. How does the power change if the wind speed increases to 10 meter per second? Did we do this? Not this one. Okay, Any idea what equation you have to put in here?
Half row A,
Exactly. Half rho A U cube. U is the velocity in this case, right? So plug and play. Double the wind speed increases the power factor by 2 to the power 3, right? Hello? Everyone with me? So that is 8. So the power would be 4.8 megawatt. Right? It's very simple. It's how many marks we have given. Okay. So that's 6 marks. That's quite a lot actually. 7 marks. That's quite a lot. Stephen is more generous. That's quite a lot for the 2 lines. Okay? Just he said the equation half A rho cube, rho U cube. That's it. And double the wind speed you get and the cubic time of this. That's it. Okay. So the next one, 4A2. The harvestable power from the wind is a strong function of the wind speed. Why the factors influence the average wind speed at a site, and how would you allow allow for the variability of wind speed when modeling an economic viability of wind turbine installation. Any suggestions?
Use the MG formula, start from there, half MG squared.
Yeah, you could do that.
Ground roughness.
No, that's also correct. Yeah. Sorry? I didn't get you.
Boundary elevations, boundary.
Yep. That's it. So everyone knows that. So why you are asking me to come? I don't know. I'm finding strange actually. Why I'm looking like a stupid actually. I'm here. Huh? So you guys knows everything, right?
No.
Come on, Declan. Huh? Right. So the strength of wind varies, and an average value for a given location does not alone depend on the amount of energy of the wind turbine could produce. So to access the frequency of wind speeds at a particular location, we can also do PDF, probability distribution function as well. And different locations will have different wind speed directions. We know that. A statistical distribution function. Did I teach you the Weibull approximation? I did, I think. Yeah, you know what is Weibull, right? Yeah, brief. What's your name? What's your name? Chris, I'm sorry, Chris. You are on blacklist. briefly, yeah. Okay, and we also know the wind power density is modified by the inclusion. So it's pretty much straightforward. Whatever you guys said a few minutes back, it's all there. Okay, and you can tailor it up. That's then 4B. An 85-meter diameter wind turbine operating in a 7 meter per second wind has a power coefficient of 0.45, right? An 85-meter diameter wind turbine operating in a 7 meter per second wind has a power coefficient of 0.45. How many of these turbines operating in a site with an average wind speed of 7 meters per second are needed to provide a minimum of 2.5 megawatt power of the grid? So what we can take here? What equation? Yeah. Do you have the answer? Did we throw the solutions with you guys? No? Not right? Yeah, that's correct. Half Cp rho u cube A. You know everything. Everything is given here, actually. So all you need is, you need to know the equation half Cp rho u cube A, and then you get out of how much watt it is. You fill in the factor. So you'll get hit about 1.6 megawatt. That's it. Therefore 2 turbines required. Okay? So this wind energy may prevent the burning of related amount of fossil fuels. Explain what you think of saving might be. This wind energy may prevent the burning of a related amount of fossil fuels. Explain what you think the savings might be. So there will not be 1:1 saving in fossil fuel energy due to the fact that wind is an intermittent resource. You know that wind is an intermittent resource, so there won't be 1:1. There will be need a fossil fuel plant on a standby running approximately around 20 to 30% in order to be able to switch the wind. This we discussed in the class, didn't we? Chris, Hayden, Declan?
No, we didn't do it in class.
Okay, Declan is again in the blacklist again. We did discuss. I did said this. Okay? So we need to always have a combination. Wind is intermittent. We need to always have a combination of fossil fuel or even other renewable, other sources to back it up. We did do this. Okay? So anyway. Could be.
No, so I'm a remote access, and if it's nothing else, I wasn't from class to hear you discuss.
Yeah, but all the things are recorded, even the wave and the wind.
Hello.
It's there in the. Did I do wind? Did I do the wind record session? No. Okay, we started from solar, is it? I did wind, right? Wind was after solar, isn't it? Before solar, is it? Okay, I'm sorry about that.
You tried to set it up, but it didn't work.
He is excusing. He's finding an excuse now. Okay, no, I'm just joking. Okay, don't worry. Okay, So I'll make sure that there's something related to that.
Okay, great.
Right, okay. So you know that's 5A, you know the answer. Sketch a tidal barrage device, explain its operation, how the average output power can be derived. I did this. Right?
Is that the title pool?
That's it.
What is the turbine?
I couldn't figure out where you get your numbers from in your example in the notes.
I'll come to you. I know, I saw your question paper. Okay. I saw your questions.
Alright.
Okay. Because I received at least 40 questions. Okay. That's why I said I need to have tutorials. Okay. Okay. So where we did the title, I don't know whether I have the notes here because this is a different lab. Lecture?
Lecture 5.
No, it's not 5. The title should be the end.
Lecture 9, slide 55.
Lecture 9. Slide 55. Oh, come on, Philip. Lecture 9. Lecture 9. See, I had the question session there. Particularly for the I could have asked more questions actually. I made a mistake. You want to do it again? Yeah, that's it. Okay? So, sketch a simple tidal barrage device, explain how it operates, how the average output power can be derived. So, you know what it is here, right? Okay? So, from this, oh my god, if I do this, then I'm stupid. Okay, that's fine. So, the tidal pool is rapidly, you know how it operates, right? You can explain how it operates. Do you want me to go? You don't want me to go through, right? Okay. So you need to have this diagram and explain how it operates. When you're having a high tide, and you can explain what is the mass per unit area of the tidal pool. Say it's about rho 2h, which we did this year. The mass per unit area covered by the tidal pool, and so you can derive from that power per unit area. So power is about 2 rho gh. That's already there, right? Rho gh, there it is. Yeah, by 6 hours, that is time, right? So power per unit area, you know what it is, right? So that's what it is. Estimate the average power output of a tidal basin with a tidal 10 marks for this. Okay, good. So estimate the average power output of a tidal basin with a tidal range of 7 meters and an area of tidal basin is given as 520. Note the tidal period is 12.5 hours and the density of water is 10,000. So it's again, power is E by T, right? So you know it's rho A R2 G by 2T. So you just need to put all these things, and then with respect to hours you will hit up 22.8 gigawatt. Okay, right. Identify and discuss key issues determining successful economic implementation of tidal energy installations.
2.8. Just in the case of that, so A is the volume of your
Area.
Is
The area of the basin is given, right? 520. That's the area.
okay.
So you put the area in. Okay? A is the area. Right? Okay. So identify and discuss the key issues determining the successful economic implementation. So this I didn't cover. Okay? But probably the guys who did wave and tidal in their assignments, they could do, but I didn't cover this. Identify and discuss successful key economic implementation of tidal energy installations. So this is one of the questions I didn't ask. Okay? Outline the overall benefits of bioenergy as a sustainable energy. This you can answer. Okay? Hello? Are you okay or? Okay. What to outline overall benefits of bioenergy as a sustainable energy supply. Right? This you can answer. I think I did quite a few things. Carbon neutral, can be harvested in liquid form for transportation applications, large choice of biomass materials that can be matched with local climate, sustainable energy sources, replenished from sun, security supply, waste materials, byproduct. You can write quite a few things. Not necessarily in this order. Okay. I'm not expecting exactly what I said. Okay? This is what? Outline the overall benefits. The benefits could be anything. Okay, not exactly like what I said you need to write that. No. It could be in some other form in the slides. This is the examination paper sent by Stephen. Okay? So that is last year. So I'm reading the one which is related to that. But the same relation I also took in the class with the different points. So you can put that one. And what are all the impacts? So you know what are all the impacts for the bio, which I've already taken in the biomass class. Okay? That's fine. A thermal biomass plant was constructed at a cost of 8 million euro. My goodness. Okay? The raw material is fresh Sitka spruce wood harvested from a local 50-hectare forest. The average harvested tree has a diameter of 30 centimeter and a length of 8 meters. The wood has 55% moisture content and an energy density of 4 kilowatt hours per kilogram and a mass of 1080 kilograms per cubic meter. The average density of trees, there's too many numbers here. Average density of trees is 2,500 trees per hectare, and the forest is thinned at 10% per annum with all woods sold. Sorry? Ah man, he's very sharp, right? We didn't do that. Okay? So I haven't asked this question. Man, look, the girl is immediately very happy. Into. Oh man. Oh. Okay, I have one more question paper with me, and then after that we can head through. Okay, so this is the semester 2 repeat of 2010-2011. You have it? Okay, how good I'm doing on time. It's 11:51, so I'll spend more 10-15 minutes in stuff. Okay, so everyone has that, right? Yeah. You have it? That's fine.
10-11, is it?
Yeah, 10-11. Yeah. Okay. You're heading off? That's very good. I like this. Okay, so all the best. So it's, I think, pretty much you know everything anyway. Okay, a proposed photovoltaic solar farm gets approximately 1400 hours of sunshine. The available sunlight has average dense intensity of 100 watt per square meter at a site. Each panel has a collection of about 1 meter square and a conversion efficiency of 10%. 10 panels are installed at the site. The capacity factor is 85%. Okay, assuming the electricity from the farm can be sold at 18 cents per kilowatt hour. What is the average annual revenue from the sun? Okay, and the second part I didn't cover. The initial cash investment is this thing. After the end, what is this selling price and what is, you know, if you, so it's like investment, initial investment, cash income and total income you need to do. But these are all the things which I haven't covered. Okay, the second part. But the first part, potentially, if I ask this question, you would be able to do. Assuming the electricity of the farm shows that this thing, what is the average annual revenue from the farm? Any idea? You know average working hours, it's 1400, right? And of sunshine. So what is the watts? Is about 100 watts. So if you multiply these together, the hour and the into 100, you will get 140,000, right? So the efficiency is given as 10%. So that's about 0.1. There's a 0.1 of 140,000 is How much 0.1 of 140,000?
40
Yeah, exactly. So 14,000. So imagine there are about 10 panels are installed, and the capacity pack factor is about 0.8 to 0.85, right? So we know the capacity factor. So the electricity generated is about, if you multiply those things, you will get electricity is about 112,000. Okay, and then that is equivalent about 10.5 megawatt per hour. Okay, and we also gave about, assuming the electricity for the farm is about 18 cents, so they're about 0.18 of the cost. So you multiply that with the income, and then you will get the thing. So this is straightforward, but I haven't done the other bit. Okay, so you know what is the, explain the term declination angle from the earth. Listen, explain the term declination angle of the earth. How does it relate to efficiency of a solar cell? How might you optimize the panels accordingly? This is there in the solar panel class. Sorry, not solar panel class, solar photovoltaic class. Right? I want to hear the noise. Yeah. This is recorded, Declan. Okay? So, I don't think I will do this. Okay? Right? Where I am now. Yeah, okay. Discuss the primary factors affecting the amount of available radiation for conversion of electricity for a site. We did that. Did we? Discuss the primary factors affecting the amount of available radiation conversion. So, at one point of time, I also put the energy budget curve. Rayleigh scattering, different scattering taking place. Did I or not? So that's what it is. So that is what the factors that is affecting. Primary factors affecting the available radiation, right? There are absorption, huh? Cloud cover, yeah, you can say cloud cover, but you have to explain in science. You cannot just say, guys, come to Ireland, I have a lot of cloud cover. Yeah. So it's absorption of ozone, absorption of uniform mixed amount of gases, CO2 and O2, it's all mentioned there.
The distance from the equator is affected.
Say again, sorry?
Your distance from the equator affected.
Yeah. Aerosol particles, I think I put aerosol particles as well if I remember. Aerosol particles, and as he mentioned about high clouds and cirrus types, scattering and absorption of wavelength dependence. So I explained this as well. Okay? Right. Okay. Let's move on. The fluctuating nature of renewable energy sources mean that significant storage capacity is required. Explain why this is Explain why this is the case by sketching the typical energy demand diagram for 24-hour period. I covered this.
Yep.
So energy band diagram, that is clear, 24-hour, how the fluctuation happens. Right? Midday, morning, afternoon, evening. Yeah? That's fine. Okay. That's what I said, you don't need me at all. You know better than me actually after this. Okay, we are in 2B, right? Or 2B, yeah. A pumped storage, am I in 2B? Yeah. A pumped storage facility is proposed for construction in west of Ireland to store excess power generated from wind farms in the area. A potential location has been identified with head height of 250 meter between the upper and lower lakes. The turbines with an efficiency of 90% will be utilized in the construction. What volume of water is required? So volume is nothing but power divided by rho g, and height, and also what it has given, the what are the things, the pumped storage facility, the efficiency is given 90%. So I have given what the pumped storage is proposed in the construction of the potential location has been identified. The height is 250 meters, and the efficiency is there 90%, that is epsilon, and the volume of water is given. Okay, so the equation is volume per second is nothing but power divided by rho g, h, and epsilon. So that is efficiency. So the power is 12 into 10 power 9 divided by 1000. You know the what is the density, and 9.8 is the g, and h is 250, and efficiency is 0.9. So you just multiply. You do the mathematics. You get volume per second, and then you multiply into hours, right? 3,600, right? That's seconds. So you will get volume in total. Right? Hello?
Where's wrong with
Sorry?
Where is wrong with
I'll kill you. What is the water density? 1000. Density of water is 1000. You don't need rho.
So what are the,
I'm not going to give this.
what are the numbers? Did you give answers?
Sorry, say again?
Did you give the answer?
Answer, you need an answer. A number. 19.6 into 10 power 6 meter cube. Cubic meter.
0.6 with
10 power 6. 6 meter cube. Cubic meter. Okay? Okay, we move on to, this is something, so what are all the three most important criteria by which storage solutions are judged? In the context, discuss some current and emerging economical storage solutions. Okay? What are the three most important criteria by which energy storage solutions are judged? In this context, discuss some current and emerging economical storage solutions. Okay. So the 2C is, I'll go through this. Three important criteria: energy density, how much energy is stored per kilo of storage system. How much energy is stored per kilo of storage system. Okay, that is the first criteria. Efficiency, right? We always talk about efficiency in our class, in the storage, right? Whatever you store in batteries, you store in different hydrogen storage, whatever it is, efficiency is important. How much energy can you get back per energy put in? It's a feedback loop. It's like making money. How much money I'm going to put it in the bank, how much returns I get. Right? It is the same thing. So if you think that those are all the critical parameters, efficiency, lifetime, okay, again go back. How much cycles? So how long if I have to invest? How many cycles of energy storage can be delivered before the energy needs to be refurbished? That's lifetime. So three critical criteria: energy density, efficiency, and lifetime. Right?
Is cost not one?
Sorry?
Cost.
You can include lifetime in that as well. See, that's what I said. Whatever I said, it's here. It's not exact. Okay, you put, if it is, that is key, if you can justify, like what I said, energy density, right? I just give a brief note on that. How much energy is stored per kilo for a storage system. I put a note there, why I'm justifying. If you put cost and justify that, then I will take that as well. Okay? Efficiency. To me, these are all the real key. Density, efficiency, and lifetime. And we are always welcome to discuss more about hydro, battery, and we also discuss flywheels as well, if I'm right in the class. Flywheels, different type of batteries as well. Okay?
So what's your definition again of energy density there?
How much energy is stored? That is what energy density, right? Per kilo system, per kilo storage system.
Per energy
It's
density?
not there.
No, I mean energy per what?
Per kilowatt.
Per kilowatt.
Yeah. Okay. Right. Question 3a. Direct sunlight of an average intensity. Direct sunlight of an average intensity of 200 watt per square centimeter is incident normally on a solar cell. The area of the cell is 0.1 square meter. What is the total incident energy in one day? How is the total energy altered if the sun falls 30 degrees? So he is effectively changing the declination angle, 30 degrees to normal to the surface. Okay? Right. So you know power is nothing but intensity into area. So it's nothing but it's how much 200 is the power is given, and area is 0.1. So if you multiply these, you get 0.002 kilowatt, right? Hello? So total instant energy is nothing but power into time. Hello? Yeah. So if you multiply 0.02 into your time is 1 day, 24 hours. So 0.48 kilowatt hour, right? And so that is for normal. If you have a 30 degrees, what you will do? You don't need me, man. E is equal to E0 of cos 30. That's it. Put cos of 30 and multiply this, you get it. Right? Yeah, that's it. 0.48 kilowatt hours. Okay? Then, 3b. Define and discuss the terms. So you have to be very careful. I'm asking you define and discuss the terms direct normal solar radiation, diffuse sky radiation, global horizontal radiation. This is done in the class.
I wasn't listening, I was thinking of something else.
No problem, Declan. Don't worry. Okay, so define and discuss the direct normal solar radiation, diffuse sky radiation, and global horizontal radiation. You want me to pull out? No, right? It is there in the slides. Okay, grand. I'm really happy for you guys. Thank you very much. Okay, what is heterojunction? How it can be used to enhance the performance of solar cells.
You didn't do that.
Are you sure?
I think so.
Did I? I haven't done the heterojunction, is it? I'll just quickly scan it through. He's very confident. Looks like that he read everything.
I don't think so. Sounds to be correct.
Let me see what I did. I've got quite a lot of questions rather than simple questions. Silicon, etching tools. Say again, sorry? What is this one? See the slide. Amorphous silicon heterostructures. Okay, so I did mention what is an heterojunction. So heterojunction is different layers of solar cells. Okay, a combination of silicon, amorphous silicon, silicon germanium, and a metal substrates, transparent conducting substrate. So it involves different layers of the materials. Okay, so probably
Just in the old notes from last year, there was a discussion on heterojunctions, and I looked here and I didn't see that discussion. I didn't take that. Slide.
you didn't see that slide at all. No.
Wow,
Okay.
I didn't.
Probably I mentioned it very briefly.
I didn't think that slide would warrant a full question. This way.
3C, right? Yeah. See, these are all like each and everything is a different solar cells, right? The tandem solar cells, it's called. Okay. But anyway, I don't want to go into detail. If I haven't touched, then I haven't asked this question. Okay. But in theory, okay, you should know this. Like, so these are all like semiconductor. Like why we need to have amorphous silicon as a different band gap when compared to silicon germanium. Okay, that's why we had the differentials. So the tunneling will be different. So the hetero means different structures. So both are structurally different, and different materials with negligible interface defects. That's one of the things which will be there. And these tandem cells are 2 or more cells which have increased absorption, which will have different capture of photons. Anyway, that's what it is. Okay, identify and discuss some major difficulties for wave power developments. Identify and discuss some of the major difficulties of wave power developments. We did this, right?
Initial investment.
Sorry?
Initial investment.
Yeah, plenty there, yeah. Yeah. Hello? Yeah? Right. That is 6 marks. What is the period and velocity of deep wave? Is it correct? What is the period and velocity of deep water wave 100-meter wavelength? Is it the same question you have as well?
Yeah.
Okay, that's fine. So, what is the period and velocity of deep water wave of 100-meter wavelength? So, any answers? Any answers? Time period? It's 2 pi w by w. That's one of the equations. Okay? So, w square, which is the velocity, which is equal to 2 pi g by lambda. So, from this, you know what is g, and you know wavelength is 100 meters, which is given. So, you will get 0.8 per second. Okay? And if you put 2 pi w by g, you get 8 seconds. That's what the time period is. Sorry? That's what you need to calculate. What is the period and velocity of the speed is, you need the value, is it? 0.8 per second. So that is 2 pi g over lambda. Okay, that gives 0.8. 2 pi, you know g is 10, make it 10, okay? And 3.14, and then lambda is 3 to 10 power 8 if you put velocity of light, so you get 0.8. For the same answer?
Yeah, for 100 meters.
What it says in the note, sorry?
Actually 10, so C is the square root of G lambda over 2 pi.
1 second. Lecture, what is it? Lecture? Wave energy, yeah. What's the number or what's the slide? Is it the one? 14, no. Yeah, if you do the square of this, what do you get? C square is equal to G lambda by 2 pi. One second. Using a typical wave of 100-meter wavelength gives a speed of about 12 meters per second or 25. Okay. C square is nothing but G lambda over 2 pi. Okay, I'll clarify this, okay? I don't know whether where this one was pulled out. Okay, I'll clarify this quickly. Okay, before this afternoon, after the class, okay? Okay, identify and explain the key design and performance criteria of wave energy device. Yeah? So, do you want me to go through all these things or identify and explain the key performance criteria?
You're gonna look into that question.
Sorry?
I think you were that's the question. That wasn't in the notes.
This wasn't in the notes. Identify and explain the key design and performance of wave energy device. Is it not in the notes?
I think wave was tidal and tidal.
Sorry?
This was.
No, I think it's not right.
Sorry? Oh, it's the same question. Okay, sorry. Yeah, that's fine. Okay. Okay, we have a repeat question there. Okay. So, calculate the power in a wind moving with the speed of 5 meters per second incident on the wind turbine with the blades 100-meter diameter. So, what equation? I think we already discussed this equation. Half is equal to A times rho V cube, right? So which gives you 0.6 megawatt. And if you are doubling the speed, how does the power change if the wind speed doubled? I mean 5 to 10. So effectively that it's 2 cube, right? So you just put the V to 2 cube, you get 4.8 megawatt. So it's straightforward 8 marks. And
It's 2 cubes.
sorry?
2 cubes, not 5 cubes.
Second, it's double. You double the wind speed, right? So 5B is okay. Estimate the power output of a wind farm. So wind farm consisting of 25 fixed pitch and constant speed turbines. The height of the hub is 85 meter and diameter is 55 meter. The wind has an average speed of 7 meters per second at height of 10 meters. The land characterized by a surface roughness of this thing. So, do you remember that we did some equation on log of Z over Z naught? Let me pull out if I have this wind slide here. What lecture is wind? 5, is it? Do you have that wind note? Do you have wind notes here?
No.
Do you have wind notes here? Okay. What's the difference between these two? Okay, looks like I didn't do this in the class. Okay? Sorry? Did I do this in the class? Yeah, I did that, yeah. Yeah, I did, but
That's the wind shear.
Like if you winch, like if you winch.
yeah, that's wind shear, yeah.
Yeah, but that's just, yeah, that's for power.
Sorry? Yeah, you can calculate from the power output from there. But I'm not seeing that in the notes, session 4. Is it session 4 or? Is that one? Both are not same? No? Yeah, you're right. That's what we have. V of Z is nothing but V reference log of Z over Z naught. So that's the formula you need to use.
How do you get
How
power
to get
from
power from that? You just, like in the lecture notes,
You just plug in the numbers with respect to your diameter. You know 55 is, what is that, 55, right? The diameter is 55 square. You know that half rho A V cube, right? That's what the power is.
yeah.
Yeah, you put those things 55 square, and then you know the height h is there. So you cube the what do you call you have height, and then if you get the fixed pitch is 25, right? 25 times half. So here will be 0.2 times 55 square, and then it's 8.3 cube. So we need to get saved. Yeah, that's what I'm trying to get you. Wait.
So do you have an answer for section 5?
It's about 346 kilowatt. Okay.
I don't understand how. One time you're saying get wind shear, and then you're saying use the rho A U cubed formula.
Rho?
You're saying a half rho A cubed U cubed. is
One
how-
second. Estimate the power
I don't
consumption.
know why it's called wind shear. I don't know why the word wind shear, but that formula, let's say it gives you a sample wind speed, and then you plug in, let's say the height you desire. It gives you wind speed at, let's say, 10 meters, and then you plug in, let's say, the wind speed you want, 80 meters, and your V, it basically gives you the wind speed at the height you're looking for.
Okay.
And then from that, you plug that, this wind speed at the height you're looking for, into rho A V cubed.
Okay. Okay. So you're calculating your U by using the wind shear. That's what you.
Yeah, that, I don't know what's called wind shear.
It's just,
basically it means to find the wind speed at a certain height, and once you find the wind speed at that height, you plug that into rho A V cubed.
Okay. Clear. I think that's within
Okay. I want to finish it quickly, okay? Identify and discuss some of the major issues restricting the development of wind energy. Okay? So the major issues are lack of robust technical information has led to opposition of wind farms, environmental concerns. You can say whatever it is, noise, shadows, flickering, wildlife. You can do whatever you like. I think we did this, okay? Financial incentives, taxations, grid connections, okay? And what else? Right. So, 6A. So, a commonly implemented geothermal harvesting technique is heat extraction from an aquifer. Describe using aid of a diagram a technique for extracting energy from an aquifer. We did this, right? Geothermal. Is it the last class? 12th or
like 11?
11?
Only about 10 minutes on it though.
Sorry?
There's only about 10 or 15 minutes time on it.
So all I need is I'm asking you to draw the aquifer and just explain the aquifer. That's it. No, just biomass and storage.
It's at the end of all.
Oh, okay. No, man.
It's the waves lecture.
Waves lecture, not on this one. Okay. Is it 10 or? Is it 10? Huh?
I think it was 10, yeah.
Lecture 10. Okay. Sorry?
There it is.
Yeah, it's here. So this is what heat extraction from the aquifer. This is a diagram, okay? And you can put whatever you like from this slide. Okay? All right. Okay. The next question is, how would you quantify the power from the aquifer? Okay? Did I put that as well? Yeah, that's what it is. How we are quantifying it. Power output, okay? So you just go through this slide. Okay. Describe with the aid of a closed loop cycle for a steam power plant.
Sorry, what's C in that?
What is CR? Good question. Is it the ratio? Heat available per unit volume of the rock is the the heat capacity of the rock, specific heat capacity of the rock. Okay. Okay. Describe using the aid of a diagram closed loop cycle for a steam power plant. I'm not sure whether I did. I did, I think. Huh? Yeah. So I think it's, I don't know where it is. So I did. Do you know where it is? So all you need is just can't use the board actually. Else I will happen. Sorry? Lecture 3. Yeah, my banner. Lecture 3 is it? Because I have notes only from 5 and above. Okay, it's just only you need to have an compressor and a turbine, and you need to have a boiler and a compressor again on top of each other. Boiler and condenser. Do you get it? Okay, I have to make a note of two things. One is the equations. Okay, and I will point it out the 6b where it is. So it is there. Which one it is? Lecture 3, and I don't have the slide here. Okay, so yeah, exactly. So I've done it in the engine section, closed cycle power plant. Okay, this is what it is exactly. So what you need to do is you need to know what is the compressor, boiler, turbine, and condenser, and then you specify the first law of thermodynamics with respect to that. Okay. I don't know what slide number. Probably from next class onwards, I need to include the slide number and the slides. Okay. Using the first law of thermodynamics, describe the efficiency of the process. That's what exactly I did in the slide. So you know what the first law of thermodynamics is: difference in heat divided by difference in work. So delta Q by delta W, which gives 0, and the efficiency is calculated by work output by work input. Okay? So pretty much I'm done. It's already 1 hour, 1.5 hours.
So will the exam follow the same structure as this?
Exactly the same structure. No change at all. Okay? You will be asked to answer how many questions? Huh?
4 out of 6.
Come on. Okay? 4 out of 6. And to be honest, when I was going through this lecture, this session, you almost know everyone knows the answer. Except a few, which we need to put in. Okay? And some controversies on the equations, which I will solve it.
One question, sorry, teacher, any question about temperature is always Kelvin, is it?
Yeah, it's always Kelvin. Or if you want to do Celsius, convert it, put it in, I don't mind. I'm not that rude, as long as we are in the same trend, that's fine with me.
Can you start to do 2 or 3 more minutes?
Okay.
First paper you did for the last year paper, 3D, the one with the ID curve and all that. I really just didn't get it.
Heterojunction, that's 3B, right? No.
3D.
Okay, IV, okay, go on.
I just didn't get the. I don't think that diagram was. I'm not sure if that.
Fill factor, is it? Fill factor or?
Yeah, it's the one where it's the voltage power against the current. Yeah, that one there. That question there. I just not sure how you get the numbers from to answer that.
So the cell has an area of 3 by 3. I can come here, no problem at all. Oh my god. I want this one.
This one is this one. 3B?
Yeah.
Still not how you do it, so.
We can have a, sorry, can I
That's
sit
okay.
here? No, that's fine. So you have been given this rectangle, right?
Yeah.
Okay. So what he's asking in 3B is the IV characteristic. The cell has an area of this thing. So he takes the things approximately from the diagram, multiplying the IV. So you mark, say this is about 0.5 or 0.4 and 110 or something.
Yeah.
Okay, you multiply that. He takes us, then you get IV approximately from the diagram. Okay, then input of the sunlight is that's your power source. Light intensity into surface area. So intensity of the light is given, right? 700 watt per square centimeter. Okay.
Yeah.
And you know the surface area is 3 by 3.
Yeah.
So if you want to convert it into meters, so 0.3 square, right?
Yeah.
That gives about 63 watts.
Okay. Yeah.
Okay. So then you calculate from this the efficiency is about 11.5, 8%. One over the other. That's input and output.
So from this I and this V is which I and which V here, like.
Sorry, this is the I, right? I. This is the voltage V.
I know, but like to which, like what
Point
value of I are you multiplying by what value of V?
See, you can take approximate values here and here from the triangle.
Oh yeah, so it's whatever,
yeah,
for whatever
the
mass
cross section exactly here.
So it's the, let's say the peak of this curve, and you get your corresponding I, corresponding
corresponding
V,
V,
and that's
yeah.
what you multiply
Multiply.
to get
Mm.
74.6.
Yeah, approximately, yeah, you take the values, yeah, 120 into something.
Yeah.
Okay, so 5, it's just an approximation, you can make 75, whatever it is. So you divide one over the other, get the efficiency, okay?
Okay.
And then you know that efficiency, then from that you calculate the fill factor with the input
Okay,
and output.
700, so that's 0.6.
3 watts.
So you're dividing.
Mm. Yeah, if you divide one over, probably I'll stop this.
Where does the ohms come into all that then? Is it used at all?